Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Introduce Mani Reiner, who is currently with both NASA Ames Research and the University of Geneva. And today he's going to present a voice-enabled procedure navigator for the International Space Station, or in short, speech in space.
Thank you. Okay, I think the title on the first slide may not be the same as the one in the call, but yeah, this is a talk we've been giving several times this year already. So it's work that we've been doing for the last 3 years at NASA Ames Research Center. It's been a fairly large project. The parts I'm going to be talking about today, mostly myself and the 5 people you can see at the bottom of the screen: Beth Ann Hockey, Kim Farrell, Nikos Kostakisafis, Jean-Michel Renders. Jean-Michel's actually not at Ames. He's been working from Xerox Research Grenoble. And then there's a bunch of other people who've also been involved in the project, whose names I'm listing here. So I'm going to start off by giving you an overview of the project, Clarissa project. Then I'm going to be talking about several specific topics which came up, specific technical topics came up in the course of building this application. So what are we trying to do? Well, this project came out of a couple of visits to Johnson Space Center in 2001 and 2002. So the history is, Ames had just started up a spoken dialogue group, and at first we had all sorts of wonderful ideas about what we thought we would do to help the astronauts and other people at NASA. And then someone came up with an even better idea. We should go to the astronauts and ask them what they wanted. So they went along to the astronauts and said, well, guys, we have speech technology, and you know, you can do speech recognition and speech synthesis and these various other things, and how could we use that to make your lives easier? And the astronaut said, well, actually an astronaut's life is you spend most of your day just working through procedures. There are literally thousands of different procedures, which are usually kept as PDF files on a laptop. And mission control is constantly telling you, you know, go and execute procedure 3,215, starting at step 7 and continuing until step 16, and then switch to you know, procedure 3,405. They're always doing this, and there's no very good way of doing it at the moment. Typically you have the laptop, which is velcroed down to a support somewhere on the station, and you're looking at the laptop, and then you switch your attention to whatever it is you're doing. Then when you've done the one step, you go back to the laptop, you flip to the next step. It's really inefficient and difficult. So I said, you know, can speech technology be used to make life easier for us? And we said, sure, that's very easy. It'll take us 2 months. And you know, 3 years later, we had something we could actually deploy. So what we have here is a voice-enabled procedure browser. You operate by one astronaut. I said the astronauts who were particularly helpful in getting us getting this thing started, pushing it through the approvals process and giving us detailed feedback on what it was we needed. Mike Fink, who actually was on the space station a year ago, and TJ Creamer, who's sort of their the astronauts interface to the nerd world. And actually, the last bullet point there is out of date. I gave this talk a while ago. It was originally planned that we would do a test deploy on the space station January to April of this year. In actual fact, we got it installed in January of this year. We didn't actually get to test it until somewhat later. I'll get to that a little bit later in the talk. So at the start of the project, we didn't have a very clear idea of exactly what it was we were trying to achieve. This was all new ground to us and to everyone. Throughout the project, I think we came up with like four key goals. So first of all, I think we were planning in terms of like just 1 or 2 procedures and a hard-coded architecture. Pretty soon we realized that was a stupid idea. We really wanted to have a general procedure-independent browser where the procedures are data that you can just feed in. And if in our architecture procedures, oops, what did I do? procedures are XML data files. We explained to the astronauts early on that there's always this trade-off between efficiency and coverage. The more you want your recognizer to handle, the less efficiently it's going to do it. So we asked them where they'd want this trade-off, and they said they definitely wanted the trade-off towards the efficiency end. They would rather they'd rather sacrifice coverage to get more efficiency, up to a point, of course. I mean, you don't want to push this thing too far. Hands-free operation is absolutely essential. The whole point of the Clarissa procedure browser is that they can be doing whatever it is they're doing while talking to the system, not having to use their hands to scroll or do anything like that. So we can't do push to talk. It must be an open mic interface. The system's always listening to you, and it should respond when we give a command. And given that speech technology, as everyone here knows, is very far from perfect, no matter how much you tune it, and the space station's background noise is space station is very, very noisy. In places it's 70 decibels background noise. You have to have, it has to be easy to correct misrecognitions.
What is that background noise?
In the Russian parts of the station, it's 70 decibels. The fans, yeah. I'm not quite sure what makes all the noise. There's all sorts of machinery there, and it's not very well shielded.
So is the heat of the air about the same as on Earth?
Yes.
So there's no helium effect?
No, it's not helium. No,
once you do the moon, I mean, if they land on the moon, they will have this effect.
On the moon? Is that right?
No.
I don't think so. It's microgravity on the space station. I don't think that. Yeah.
But in general, this is acoustic noise, not electrical noise.
It's acoustic noise, yeah.
But since you don't have that many astronauts, right? You can use something like a speaker-dependent model.
Well, we did consider doing that, and actually we're very glad we didn't, because the people who were meant to test Clarissa weren't the ones who actually ended up testing it. If we'd done speaker adaptation, we would really have been in trouble.
What is the variety of accents that you get? I mean, these are all Americans?
Yeah, that's an embarrassing topic. Originally, we were planning to have it work with both American and Russian accents. And one of the reasons we hired Nikos Chrisafis is that he's an expert in dialect adaptation. He did his master's in that under Vasilis Tigilakis. And we were going to build a Russian accented, a set of Russian accented language models, but in fact we never managed to get enough training data together, and it didn't happen. It was really bad planning on our part. But later on, we do hope we're going to have it working well with Russian accented English. I mean, we know exactly how to do it. We just don't have the training data. But it wouldn't be very hard to get hold of that training data if we were just, if we just had a little bit more time, we would have done it.
So for now, the Americans are going to do the work on the station, right?
It'll be an American test. We've already got test deploys so far. We're just at the level of doing a few experiments. Okay, so I'll just go on and tell a little bit more about what our key objectives are about. So we supply our procedures, as I said, as XML data files, and one of the absolute key requirements we didn't even realize at the beginning of the project how important this was going to be is that the XML has to capture all the information in the current paper or PDF procedures. And the reason that we have to do that is that the operations personnel at Houston have to be convinced that we haven't changed the procedures on them. These procedures are often extremely important, safety-critical things. And there's this very complicated sign-off process where they they ascertain that the thing meets all the criteria that have been imposed. And we do absolutely not have the freedom to change anything in those procedures. So we have to convince these professionally paranoid people that what we've done is still safe. That was a bunch of interesting challenges we'll get to in a minute. Okay, so high-performance recognition, as I said, we wanted to go towards the end where you get high-performance recognition and maybe fairly constrained language. And astronauts are pretty good subjects for that. Most of these guys are former Air Force pilots, and they've been trained to use controlled language. They find it very natural to use controlled language. And so they told us that if it's a kind of controlled language that they've been taught at flight school, that's absolutely fine. And you'll see when I demo the system shortly that it's that kind of language.
This is just to navigate the manuals and all these procedures. No actions are taken. It's not like the astronaut says, turn this knob to the right. And
no,
none of that, right?
None of that, no.
So there's clear error checking here. Like the astronaut can see whether the recognition got him to the right page and he's
Yes.
the right thing, right?
No, we didn't think that the thing was actually very risky, but these guys, as I said, they are professionally paranoid. They came up with most bizarre objections. I think my favorite one was this guy who said that he was worried that a cosmic ray might hit the program counter. He said, you know, he clearly was from an earlier age of computer science. He thought that there was this location somewhere in memory which held the number of the step you're currently on. He says, supposing that gets hit by a cosmic ray, you might jump to the wrong step and something bad might happen. So we actually had to store the location of the current step in two places and signal an error if they were different. You know, if that happens, we signal an error saying, you know, possible cosmic ray incident. I really actually did this.
I mean, have some confirmation every time, whatever you say.
It doesn't give you confirmation, but it does give you, no. We asked if they wanted confirmation. Actually, I'll get to that as well in a moment. There is a mode in which it's even more conservative, and it does check that everything's been done. But no, I'll show you that by and by.
But if you were to browse them by hand, you would still have this problem, right? If the cosmic rays hit the laptop and you get a different number there, how are you going to know?
Well, I don't know. Maybe they have cosmic ray checking in their laptops, or maybe the guy was just, 20 years out of date. We just did it. We didn't argue. A lot of the time, when you're dealing with operations people, you have to have that attitude because they run the show, and if they don't like it, you don't do it. Okay, here's a picture of Beth Ann Hockey, who's project lead, training Leroy Chow, who's one of the astronauts who's been on the station, just came down recently, showing him how to use Clarissa. Okay, so hands-free operations, another second key goal. So I said the whole point is we want to be hands-free and eyes-free, so we have to have push-to-talk. And that immediately gets into the problem of how do you identify crosstalk, which is a classification task. And I'll be telling you a lot about how we did that later on in the talk. But yeah, that was extremely central. Yeah, and as I said, you've always got misrecognitions because of noisy background and so on. And so you have to be able to undo or correct commands. So we designed the whole dialogue management architecture with the idea that undos and corrections will be very easy and robust. So you can always say undo, you can always say no, I said, no, I meant, and repeat your command. And I'll show you examples of that shortly.
So what should happen?
It's a technical term often used at NASA. Things go wrong. Okay, well, maybe this is a good point for me to give a short demo so you can see how the thing actually works. Let me try and do that. Now, let me see. I do PC3, both screens. Oh. Except this now. No, that didn't work. That's good. Help.
To start, say load and a procedure name. For example,
Stop.
say load EMU.
So as you see, it's barge in, and yeah, the astronauts definitely wanted barge in at an early stage. And it's also open mic. It's not reacting to anything I'm saying, as you see. Load training procedure.
Do you want to restore the saved variable values?
No.
Starting procedure. Clarissa training. Objective.
So this is the embedded training procedure. This is the only one the astronauts have actually done so far on the station. They tested this back in June. So I'll do a couple of steps of this and I'll show you a real procedure. Go on.
Step 1. Say increase volume or decrease volume as needed, then say next.
Increase volume.
Output volume now set to 60%.
Go on.
Step title, navigation. Step 2.1.
Stop.
In this section, you will practice.
So I'll try moving around a little bit so you can see how navigation works. I won't follow all the instructions, the training procedure, because they're a bit tedious. Go to step 2.5.
Step 2.5.
I meant 2.6.
Say acknowledge. Step
So you see, I did the correction like that.
6.
Go to
All of the
2.8.
above are synonyms that will take step 2.9.
I said 2.8.
More detailed help on a topic is
I said
available by
2.8.
saying help on some topic. Step
Nope, it's really not getting that.
2.10.
Go to step 2.8.
Step 2.8. For context-sensitive help, you may say
Stop.
help at any time.
Close procedure.
Do you want to close?
Yes.
Clarissa, closing current procedure.
Load coliform detection procedure.
Starting procedure.
This is a real
In-flight
procedure. It's the one
coliform
that
detection.
they're actually going to be using.
October 19th, 2004
Stop.
version. Object.
Go on.
Note, before step 1.
Where
There's
are
a
we?
voice note. We are at note, before step 1.
Go on.
Step 1. Reference the IMS database. Unsto Microbiology Water Analysis Kit. Refer to Figure 1.
Stop.
Verify that the expert...
So this is a fairly typical procedure. They're asked to get out some equipment and then do a number of tests. Here they're going to be testing their drinking water to check that it hasn't been infected with microorganisms. So you can just do simple navigation around the procedure, and you can also preview Steps that you haven't yet got to if you want to. So let me show you how you do that.
Note,
I have a
Stop.
question about this.
before step...
Sorry?
You said in your previous slide that this was a hands and eyes free operation.
Yeah, that's right.
And you're skipping to step 2.8. Do you assume the astronauts know that there's a step 2.8, or that they have the procedure memorized? Or
Typically, mission control will be telling them they should skip to a step. They'll be telling them, you start this step and then you want to miss out a few steps. That's the main reason we have that command.
okay. So there's somebody with a hard copy that knows
Someone
a location to go to.
in
Objective.
Houston, stop.
Before step 1. There is a
Stop.
voice note. This procedure...
Yeah, typically someone in Houston is looking at a copy of the procedure, and they're following them.
Can't the guys on the ground actually just open the procedures at the point where the astronauts should start working for them? I mean, why can't they just press the button here as opposed to up on the station?
They could open them, but I think that tracking them step by step while the astronauts are doing them will be pretty difficult. I think the astronaut wants to have a little more fine-grained control. Also, you have problems going to Earth's shadow when you're out of contact, and you have to swap around in different operation centers, and I think that will be very difficult.
You said in your other slides that the system uses open microphone.
Yes.
So performance probably will be as low as the one you're doing there.
I'm using open microphone now.
Open, that means it's not closed talk, but...
No, by open microphone I mean that it's always listening, it's not push to talk.
Oh, the way you're okay.
But they wear the headset.
Okay.
I'm sorry?
They wear that headset when they work with the system.
In fact, they wear a Bose headset, but yes, in principle. I'm not wearing a Bose because they're heavy and bulky and they hurt my ears. The astronauts hate them. Let me show you previewing then.
Objective.
Stop.
Before step
Stop.
1.
Preview step 7.
Review mode. Step 7.
So you see it's
Remove
showing
one
me
microsample
2
inside
screens here.
analysis bag from temporary stowage.
Go on.
Review mode. Step 8. There is a voice note. Gently swing
Where are we?
microsample inside. We are reviewing. Step 8. We are at objective. Before step 1.
So it's telling me that I'm reviewing one step and I'm actually on another step. Exit review mode.
Exiting review mode.
Okay, so you get the basic idea of what it does. I think I'll just go back to the talk, and I can certainly demo this more later on if people are interested. Close procedure. Yes. Okay, so I'll get on to the specific technical issues that we're addressing here. So as I said, first of all, there's the problem of how you write voice-navigable documents. And I must say, when we started doing this and we looked around, we were kind of surprised how few people there were that had actually gone and tried to do this thing, taking a formal document in written form and turning it into a corresponding voice document. And I think one of the few groups that's really looked at this is the guys at Alex Rudnitsky at CMU. They've been looking at aviation manuals. But you know, I think we're probably the first people who've really had to look at this in detail and make it work in a deployed project. And I mean, none of the problems are going to be very surprising to people. Everyone knows that, you know, voice and text are different modalities, you have different conventions, and voice has lower bandwidth than text. And you know, all these things that you are well aware of. But when you start looking through the implications of that, it does get a bit scary. So here's an example. This is actually from a procedure that we were hoping would be used on the space station. It's for checking the American spacesuits. We were very disappointed that it didn't get used because apparently the American spacesuits are all broken at the moment, and they aren't in a position to test them. Another piece of fallout from the Columbia disaster. They haven't been able to bring up enough supplies to fix these things. So here are some steps from the EMU, I can't remember what EMU stands for. It means spacesuit. So you're at this step, and well, you can see what it says on the paper copy. Clarissa will have to ask you some extra questions. The way this procedure works is that you might be checking up to 3 spacesuits at a time. So at the top of the paper copy it says this procedure can be valid for 1 to 3 suits, and you should adjust the instructions accordingly. And of course, an astronaut's very clever and capable, and he'll just automatically know how to interpret the instructions depending on how many suits that they're working on. And Clarissa's an automated system, so it has to be completely explicit about everything. You know, instead of relying on the astronaut's intelligence just to help them out, it has to say, you know, do this for suit 1, do this for suit 2. So right at the beginning, you have to insert a question where it says, you know, are you working on EMU 1? Are you working on the first suit? Are you working on EMU 2? And are you working on EMU 3? And then, you know, when you get to step 20 at the bottom half of the screen, you've got this table where you have to fill in the suit pressure and check that it's in the right range, 0.4 to 1.4. You fill in this table, and well, on the paper version, you've got a table where you've got 3 squares for the 3 suits you might be checking, and on the Clarissa version, it has to be asking you 1 to 3 questions depending on how many suits you're working with. So if you're working on the first suit, it asks you what the suit pressure is for EMU 1, and then it fills that in the table. I can show you that a little bit later on if you like. We've got an example of a table in our training procedure. And then if you work on the second suit, it asks you that question again, and so on. And all this, it sounds trivial, but we had to take these procedures and we had to add in the extra information so that you could convert them from paper documents into voice documents, which it actually turned out to be more work than we'd expected it to be. So here's another example of that. This is a bit where there's a component of the spacesuit called an LCVG, which should be filled with water. And if it's dry, if it's out of water, you have to go to a sub-procedure for filling the LCVG. And you know, depending on how many spacesuits you're working on and which ones are out of water, you may be working on 3 suits, maybe only one of them's out of water. So of course, with humans, they're smart enough to figure all that out. But with Clarissa, you have to put in all this control logic where it says, check which suits there are, check which ones are out of water, jump to the right piece of procedure, and then say for the ones that are out of water that you have to do this filling procedure. And like I said, in principle, not very difficult. In practice, there are just so many details to get right, and then you have to convince all the safety people that they really are the same as the procedure. So we ended up having to put in quite a lot of extra constructs into the XML that we're using to write the Clarissa procedures to handle those conditional logics. We have branch points, we have questions to the users. You had me, it was asking some questions when I give the demo. You're asking yes/no questions at many points. You're asking questions for numerical input when you're filling in tables, which they often do. There are steps whose content is conditional on the settings of variables, and then you can jump to sub-procedures, as in the slide I just showed you. So there are, and as I said, when we started doing this, we discovered problems we hadn't first thought of. You have this, you're setting variables in the course of executing the procedure, and steps can be conditional on the value of variables that you acquired earlier on. And you've also got the problem that you can jump back and forwards inside the procedure. So there is the problem that potentially you can arrive at a situation where the action taken on a step depends on the value of a variable that hasn't yet been set. And so we had to put in more logic in the procedure browser, which said that if that happens, you hit an unbound variable because you're executing the steps in an order which isn't the one that the procedure writer anticipated. You have to get a warning that you probably need to execute the earlier step, which sets the variable, and that's potentially quite a difficult problem, even though it sounds kind of stupid. So I guess there's a lot of these little problems, and I guess the take-home I'm trying to give you here is it's not as straightforward as you think to turn a text document into an interactive audio document. There's a lot more problems than you first believe they're going to be.
General question?
Yeah.
Have the astronauts been through these procedures before, and this is kind of reminding them of the steps?
The astronauts get trained on all their procedures. I mean, an astronaut's training schedule is just unbelievably packed. I think they're trained on all the procedures that they might have to execute. But I think that training is often, it's often just one run through the procedure. These guys are so unbelievably capable. They do seem to be able to learn them fairly well from that one run through. We were just amazed when we trained them on the use of Clarissa. We were given 45 minutes to train them, and they were pretty good after 45 minutes. They weren't quite as good as we were, but not far off. We were pretty impressed. So yeah, as I said, we had a lot of problems with sign-off procedure. These things are signed off after a lot of work, and extending this to voice documents really wasn't a straightforward job. So I don't think that, well, I think we did well enough that we got the things signed off, which we were pleased with, of course. In future, I think that there's a whole new area here which would need to be systematically researched in I think it's a sort of interaction of multimedia and program validation. You really would like to be able to do formal proofs that, irrespective of how you execute the procedure, how you jump around in it, no bad things are going to happen. We weren't able to do that in a systematic way. We just showed people samples of how you different paths through the procedure, which when we showed them enough samples that they were willing to concede that it seemed very unlikely that any bad thing would happen. If we were doing this with all the procedures on the space station, all 12,000 procedures they have, I think that the people in Houston would be demanding formal validation. So again, you really would like to have some way of doing that using formal validation methods. And yeah, I think that's an interesting challenge for someone who's got that background. Okay, so as I said, this part of it was completely unexpected and much harder than we thought it was going to be. All right, so I'm going to get on to the next topic of how we do the actual recognition. This is perhaps something closer to what most people here are actually interested in. So you've seen examples of some of the things that you can say to the system. You can navigate around, change the volume, you can undo and correct. I didn't show you some of the other things. You can set and cancel voice alarms. The astronauts, they're often having to set alarms and timers to schedule their activities. You could also record and play voice notes on different steps, and I could show you that later on. All in all, we've got about, I think about 75 different functions, and the total vocabulary is about 260 words. So, at the start of the project, we had to make a choice as to what recognition architecture to use. We didn't have any training data, which is pretty usual for a real deployed project. It's not, it's not ATIS or anything like that. No one's ever developed this particular application before. And we had a fair amount of experience with grammar-based recognition, so we decided we'd use a grammar-based architecture. One of the problems is they often do change the requirements on you, and you have to be able to respond flexibly to that. So what we've developed is an example-based grammar construction architecture. And this is something we've actually deployed over we've shared this over a number of projects, and Clarissa's just one of them. We've got this program called, this platform called Regulus, which we've been developing both at NAS and at the University of Geneva and also some other places, where what we're trying to do is maximally enhance our ability to reuse recognition grammars of multiple applications. So what we have is one single application-independent unification grammar. It's a very general grammar for speech applications, which is just based on linguistic principles. And then we have example-based methods that can derive application-specific unification grammars out of the single central general grammar, and then we can compile those specialized unification grammars into context-free CFG language models, which will run on Nuance. We compile them into GSL for people who know the Nuance platform. And we're getting reasonable performance on that on real tasks. I've got another application from Geneva. If we've got time, I might show you that briefly. So this is the picture. We start off with our it's working. We start off with our large English unification grammar here. We use explanation-based learning to specialize that to an application specific. We compile that down to a GSL grammar, and the Nuance compiler turns that into a recognizer.
So use unification grammar instead of CFG grammar easier to write?
Yeah, unification grammar is very compact. So our general grammar is less than 200 rules, but it's got a large chunk of the basic constructions of English. There's a lot of grammar in that. And yeah.
Am I interrupting?
Sure. No.
So what made you decide on Nuance?
I guess because several of the people from the project come from SRI, and we were kind of used to that software base. I mean, I think that we had a positive experience as well with the Command Talk project they did at SRI, where they pioneered this architecture, writing the grammar as a unification grammar, and then compiling it down into Nuance form. And that was a very successful project, and it gave us I think it showed you could do this kind of thing. We've tried to take that approach a bit further in Regulus, but
you convert that to CFG.
Yeah. We can't. I mean, obviously, you can't. Well, at least I've never heard of anyone who could do recognition using unification grammar. I think it would be a very challenging thing to do. Yeah. What? Sorry.
More SRI did.
Well, we're certainly building on Bob Moore's work. I mean, he did the same thing with Gemini, starting off as unification grammar and compiling it into GSL. But we have slightly different ways of doing the compilation. But yeah, we're certainly building on Bob's work.
So the task is comparable to ATIS, which is larger?
Well, the Clarissa task is much simpler than ATIS. I'll show you our Geneva application later on. And I think that's a considerably harder task, this medical speech translation task, and I think that's not so far from ATIS. It's not clear to me which is harder, in fact. Okay, so Regulus is an open source system for people who are interested in playing with it. So you can get it from this URL over here. And there's a development environment, and in fact, we're bringing out a book on it next year. We've nearly finished writing that. So, a lot of people ask us, you build this in a grammar-based way, and is the grammar-based approach actually better than a mainstream SLM approach? We gave a paper at InterSpeech a couple of weeks ago where we were doing the same kind of experiments here as we were doing with we did these comparison experiments. You build a Regulus recognized, you build an SLM, and you try and compare them. So this is actually fairly similar to our InterSpeech paper. So what we're doing, the basic idea behind doing the comparison is, since Regulus is data-driven, you've got this example corpus you're using to extract the specialized grammar from the general grammar, you could use that same corpus to build an SLM if you wanted to. And then you can, since the whole problem here is you're short of training data, and the reason we're using the grammar-based thing in the first place is that we're short of training data. The question is, given a certain amount of training data, which architecture is going to give you the best results?
Well, yes, but the astronauts, since somehow they have to know what kind of they can say, what kind of they cannot say.
Yes, that's right.
So, but that, burden on the astronaut.
Well, as I said, we told the astronauts what the story was, that that we could give them more coverage, but that would probably give them worse performance, and so they're used to this kind of thing. And when you think of the variety of ways in which you could phrase these commands, I think if you gave people complete freedom to phrase them any way they wanted to, you would have trouble getting good performance.
They have to tell them.
They do a 1-hour training procedure on the use of the system, and after that they seem pretty comfortable with it. And also, we talk to them. We've adapted the language, the kind of language they're used to from an aviation background, so the commands are natural to them. Anyway, so we did experiments comparing the performance. Let's see. So what we're doing is we're extracting semantics in both versions, and we're trying to do a head-to-head comparison to see which one works best. So here, our semantic representations look like this. So the lists of semantic atoms. So like go to step 3.1 is a list of 2 atoms that go to in 3.1. No, it's the next step is correction and next, and so on. And then we have phrase spotting rules, which can either match. You can have things here, basically regular expressions, which are matching surface strings. Then you can also, in the Regulus version, you can have patterns which match the logical forms too. So you have you can extract information from either the surface strings or the logical forms. And then what we did was we trained the recognizer and the semantic analyzers. We have here we've got a semantic analyzer, which I'm not going to go into the details of, which gives you these patterns and which uses statistical methods to try and find the most associations between patterns and semantic atoms. So we trained it on a bit over 3,000 utterances of text data, and then we evaluated on a bunch of recorded speech data. And we tried different combinations of how we did the recognition. We tried simulated perfect recognition, it was just text. We tried the grammar-based language model using Regulus. We tried the statistical language model built using Nuance Say Anything. Nuance Say Anything is actually pretty much the SRI LM toolkit with a slightly more user-friendly shell on top. And then we tried different combinations of patterns. We had string-based regular expression matching, logical form patterns, and both. So our results were, here's the results for word error rate and sentence error rate. So the GLM is a bit better than the SLM in terms of word error rate. The difference is larger in terms of sentence error rate. And here's the results for semantic error rates, understanding performance. So here we've got this column over here is rejections, so the system just didn't get anything. These are incorrect understanding, and the total in the last column. So for text, we're getting about 3.6% if we use just one of the knowledge sources, going down to 1.6 if we combine them. So it's a fairly easy domain, as you can see. If you're getting your like 98.5% correct performance. For the SLM, we're getting about 10% error rate using. Since it's an SLM, we're only able to use. We're only producing strings. We're not producing any logical forms. So we're limited to surface patterns, string matching. And for the grammar-based language model, the Regulus one, we're getting about 7.7% for surface patterns, for regular expressions, 6.3% if we use the logical form patterns, and 6% when we combine them. So this is clearly our best result. So if you compare those things, just summarizing, the more you get towards understanding, the bigger the difference between the two architectures gets. So we're getting over here, on word error rate, there's a 15% relative difference between the grammar-based recognizer and the statistical recognizer. You move to sentence error rate, it's 21% relative, and when you get to semantic error rate, it's 38% relative. And we don't think this is because the semantic understanding architecture is unfairly biased towards logical forms as opposed to surface patterns. As you see over here, we're using logical forms against surface patterns on text input, and the difference is pretty small. As far as we can see, the advantage of the grammar-based approach is that the semantics are much more tightly integrated into the recognition. It's all coming out of the same grammar, so you get better synergy between them, and that does seem to give you a lower error rate. I mean, we'd like to do more experiments. We get similar kinds of results out of our speech translation application as well. So, our tentative conclusion is that for this kind of application where you've got users who are happy with constrained vocabulary and you've got relatively small amounts of training data, grammar-based does seem to be quite a good way to build them. Okay, so that was. Were there any questions about recognition before I get on to the next topic?
So what has been done when you do the example-based learning?
So
you use the example-based approach to customize the unified
yes,
grammar, right?
That's right.
What kind of things have been done?
What
kind of approach are you using, basically?
So
just adjust the probabilities between.
No, we have two training phases, in fact. First of all, we have this very big unification grammar. Just go back a few slides. So we have this big unification grammar over here. This is just a general unification grammar for English. It's something you couldn't possibly compile into a recognize. We tried compiling to recognize, and the recognize is I mean, you actually can do it if you ignore some of the features, but the recognize is completely unusable. It's so under constrained that it just doesn't recognize anything. So what you do is you basically you're extracting out a subset of that unification grammar and compacting it into a sort of flatter and simpler form. As I said, we've got a book about this which we've nearly finished. I'm very happy to send you a copy of the manuscript if you want to know more about this. So you produce this GSL grammar, and in the nuance compilation phase, we do probabilistic tuning. We use the training corpus the second time to do probabilistic tuning of the grammar, so it's actually turning to a probabilistic GSL grammar.
Okay, so in the first step, we only extract the words.
The first step here is creating a simpler unification grammar out of the. This is a general application independent unification grammar. So we've got training corpus, and that's turning it into much simpler application specific unification grammar.
Okay. So roughly how many rules are there?
So the first one is about, I think it's currently about 185 rules. Now, the application-specific grammar has probably got about as many rules. It actually may have more rules, but they're rules, they're simpler, flatter rules. So it's expanding that grammar out into a simple, flat.
And have they converted to CFG coloring?
Typically about 2,000 or 3,000. Yeah.
So how much data did you use to customize your graph?
Let's see, over here. So for these experiments, we had about a bit over 3,000 utterances of data.
Yeah, so everything now is syntax-based, right? But the rules are basically...
Well, they contain semantics as well. The rules that they produce...
I thought when you started with the English grammar,
yes.
probably just syntax.
No, it's syntax and semantics. It produces compositional semantics. The semantics is not necessarily the kind of semantics that's useful for an application, so we have to do this...
You develop it specifically for the domain.
Yeah, this semantics is not the semantics the grammar produces. We're producing the logical form. I should actually have a picture showing a logical form, but we're matching... we've got subterms of logical form, like a term volume or interjection back, and these come out of the logical form produced by the general grammar, and they get the pattern matching rules, turn them into lists of atoms. Actually, it might be good to show you the other. A little bit later, if I get to the end of the talk, I've got a little bit of time left, I'll show you the speech translation application where we use the logical forms directly.
So what is it that if the program has this advantage, so why you are the other group probably using it?
Well, it was a lot of work building this thing. Actually, we're not the only group. Several other people are using our framework now. As it's open source, it's available on the net. They're using it at Stony Brook and Australia. There's several other groups.
Because CFG is easier to...
Well, writing CFG grammars directly is very painful, as probably you know. Well,
we'll do that anyway.
Yeah.
So, is there any downside of doing the conversion? Either because maybe some of the conversion may...
Well, actually, I think there's a cultural reason as well. You say, why is no one else doing this? I mean, the kind of people who know unification grammar tend to be linguists, and the kind of people doing speech recognition tend to be engineers, and the intersection between linguists and engineers is quite small at the moment. So we built the system very much so that linguists could start doing, people who have mainstream linguistics training could start building recognizers, and linguists like it a lot. I mean, engineers don't always like unification grammar. But
the real issue is after the conversion,
yes.
Is the quality of CFG better than if somebody
hand-coded? We've done experiments where we've compared handcrafted CFGs against CFGs produced by Regulus, and they're about equally good. Regulus is often better, in fact. Building CFGs is so time-consuming, and they're so difficult to tune. I mean, obviously, it's the same as with any compiler. If you're really smart enough, you can always write a better machine code program than the compiler can, but it takes a lot of time, and a lot of very specialized effort.
So is this what your example input looks like? Those 3 lines there?
The training? Yeah, when we're training the semantic analyzer, we have things like that, yeah.
Do you have any probabilities on them, or are they just all equal probability?
We extract probabilities because, of course, many utterances get repeated. I mean, it rapidly learns the most common expressions in this domain and next and go on. It starts giving those higher probabilities, but that's part of the problem.
So it corrects at runtime for that sort of thing?
It's building a PCFG language model, so at runtime it certainly is using that information, yes. Okay, well, as I said, if people are interested in this, I've got Regulus running on this laptop over here. I'd be really happy to show you offline, more of the details of how it works. It's all open source, so you can just download it off the website and use it yourselves. Okay, so I better progress to the next topic on open mic recognition. So this is mostly work done by Jean-Michel Renders at Xerox Europe. We hooked up with him last year, and for people who don't know, he's an expert on use of machine learning, in particular support vector machine techniques, for document classification. So it seemed to us that crosstalk, identifying crosstalk is a kind of document classification task. You've got 2 different classes of results from the recognizer, and you're trying to separate them into these two buckets. One bucket is crosstalk, throw it away, and the other bucket is real command, act on it. So what the recognizer is producing is words tagged with confidence scores. And at the beginning of the thing, our intuitions were, well, if the confidence scores are low, then probably it's crosstalk, because the recognizer is clearly doesn't like it. And also, if you look at this thing, if you eyeball examples of recognizer output, you see that some words, in particular some bigrams, are suggesting crosstalk. In particular, some words with low confidence scores. If you see certain words with low confidence scores, you are inclined to believe that what you've got here is crosstalk, not real.
So you're assuming that commands can be embedded in sort of crosstalk? There's not.
No, we're not trying to. In fact, we explicitly not. We don't want to do that. We want to. If something is crosstalk, I mean, someone might be. They might be mentioning a command. They might be saying, I'm not going to say next now, and it doesn't actually trigger on that, or at least it doesn't most of the time. It gets that right.
So I'm confused about the definition of crosstalk. So is crosstalk anything you might say in a state where the recognizer should not listen to you?
But what we say,
like when you had it in stop, you said stop. Is everything you say after that considered crosstalk, for example?
Well,
not really, right?
The way the recognizer is working here is doing endpointing. It's doing silent endpointing. So if it hears anything and there's a long enough silence, it breaks off, starts recognizing the thing it heard since the last piece of silence, and analyzes that as a self-contained utterance. So it's certainly cutting the thing into chunks using the endpointing. And for each chunk, it's trying to decide whether that's a command or whether it's a piece of crosstalk. And crosstalk, I'm taking, is anything that's not commands. But usually it's people talking to someone else. On the space station, it's usually talking to the other crew member or talking to mission control.
So anything that is not in the grammar is crosstalk?
No, I'm saying that anything that's not directed to the system is crosstalk. I think it's more, the distinction I would make is more, if you're actually addressing the system, and the system, if you're addressing the system, then it's a system command, whether the system understands it or not. If you're talking to someone else, then it's crosstalk. When we've talked about this, I don't think there's complete agreement on what the term crosstalk means. Maybe some people use this word.
Endpoint detection.
Sorry?
The problem is just endpoint detection.
It's not just endpoint detection. I mean, you can have material between two endpoints, between an endpoint and the next endpoint, and maybe it's not a system command at all. You don't want the system to react to it.
For engineers, crosstalking is when you have two wires and you send a signal on one wire.
Or two persons talking.
The other signal gets corrupted from the wire next to it.
Or two persons talking simultaneously. This is at least in my understanding.
Yeah, I don't know. Maybe we use the term incorrectly, or in a way that some people. Maybe we should use a different term instead of crosstalk. I know we've had several people complain that this isn't crosstalk as they understand it. Was one a better suggestion?
Out of context, maybe, or something.
Sorry?
Out of context, or something.
But it's not so much out of context. I mean, we want to distinguish between the case where the person's addressing the system and the person's not addressing the system. And
the speaker's intention.
Sorry?
It's more like a speaker's intention. So what the person is talking to? Who the person is talking to?
I mean, I know some people are referring to this as crosstalk. I mean, we're not the only people who use the term in this way, but yeah, it would be nice to get a bit of standardization.
These parameters, when you compare with the push-to-talk system, anything that is not push-to-talk outside of that range is crosstalk.
I guess so, yeah. Yeah, but since we don't have push-to-talk, we have to try and determine when the person's addressing the system. A lot of people who watch Star Trek, they make the comment that this is, in a way we're trying to solve the problem the Star Trek computer hasn't managed to solve, because they always have to say computer, and then they give the commands. In fact, we asked the astronauts whether we'd like them, whether they'd be happy with us doing it that way, and they didn't want us to say computer. They said it's.
But in that case, they have more control, right?
They have more control. That's why.
Yeah, they don't like it because they feel like it's too robotic, right?
They just said they thought it would be too irritating, and they
depends on how good the performance is.
Exactly.
Yeah, you get a lot of control.
I think that actually the version you got here, in a moment I'll tell you what the version was, but. Okay, so let me just sort of give a little more background, and you'll see where we are. So here are examples of the kind of task we're aiming to solve with. Here are positive examples. We say previous step. The numbers are the numerical confidence scores on the words. So we have previous step, enter challenge, verify mode, read step 12, and then we have negative examples. These are all real examples. You say that. Well, that's what the recognizer produced. Most of these. In most cases, what the person said was completely different. I mean, it's forcing everything into this 260-word vocabulary using the grammar, so of course, often it's just nonsense. Now, say that, cancel it. You have very low confidence score on say, very low confidence score on it. I said, repeat row 1. So these two, you can see pretty clearly that they're bad recognition because the confidence is so low. This one's trickier because the confidence on most of the words is quite high. It's just that it doesn't actually make sense as a command.
So you put some garbage words in your grammar, right? So if you detect that actually those are the words returned, then you know them.
Well, it's not so easy to add garbage models to the recognition grammar. We tried doing that, but doing it without degrading performance is also quite challenging. I don't know. I mean, there's obviously a lot of ways to try and solve this problem. I mean, this is just. I'm not saying this is the only way to solve the crosstalk problem. I'm very far from it. But anyway, I'll tell you what we did, and we'd certainly appreciate other suggestions. So in the version I just demoed, this is actually the version that we have deployed on the station, so I thought you might be interested to see the one that we're actually using. We use this very naive system, very naive approach to crosstalk detection. We just use the average confidence score and a threshold. So if the average confidence score is lower than the threshold, we get crosstalk. And as you saw, in fact, that it gets it wrong quite a large part of the time. Unfortunately, we just didn't get this work on more sophisticated detection of crosstalk finished in time for the deployed version. If we'd had like about another 6 weeks, we would have done it, but we didn't. The classification error is about 9%. It's about every 10th time it gets it wrong, and it either gives you a false positive or a false negative. So, okay, so this is the work that Jean Michel did, treating the text classification problem, and yes, support vector machines, as probably most people here know, are very good at text classification problems. So, as you said, in the naive version, we're just using the confidence scores. We're not looking at the lexical information at all. We'd really like to use the lexical information, since some of the bigrams are suggesting that you've got a bad recognition. So you've got this very high dimensionality feature space with all the possible unordered bigrams. So one of the reasons why SVM is a very good method here is that, as I'm sure everyone knows, SVM algorithms are very, they're specifically targeted in the problem of avoiding overfitting. So where an unsophisticated learning algorithm might very easily overfit on such a large feature space, and that's a fairly small amount of training data, SVM algorithms do pretty well. So specifically, we use the SVM Lite package, which is a well-known freeware package you can get off the web for research purposes. And Jean-Michel adapted the SVM. Well, SVM Lite's been used, it was originally developed for document classification. So in order to adapt this for this new task of detecting, distinguishing between different kinds of recognition results, the two main things he had to do were, first of all, to get an appropriate kernel function, and then to take account of asymmetric costs, because it's clear that false positives, the system reacting when you haven't spoken, is considerably worse than false negative. We're actually in the middle of doing experiments. We videotape people using the system, and we actually count the cost in terms of lost time for a false positive and a false negative. And intuitively, if you get a false positive, the system reacts, you didn't speak. You have to correct it. You have to notice it's reacted and then correct it. If the false negative, it doesn't react, you did speak.
So
yeah?
It's only more complicated document classification because you have to know how long your document lasts.
Yeah.
It is embedded to one stream.
Well,
cross-talking and...
No, we're assuming it's been cut into chunks by the endpointing. We're just taking each chunk and trying to decide whether that... No, the endpointing is doing that. We're not separating into chunks. The recognizer's already done that for us. So yeah, as I said, false accepts, they take more time to correct than false reject. The false reject, you just say it again, which is very quick. For false accept, you have to notice, and you have to correct, and so on. It clearly takes longer. So let's just look at kernel functions first. So what we have is basically a weighted bag of words model. We have words tagged by confidence scores. And we also added a feature for the global confidence score. The global confidence score is just the average of all the confidence scores. So a sentence is mapped into a point in v plus one dimensional space for v's vocabulary size. And then we experiment with a number of different kernel functions. So linear kernel, linear is just weighted unigrams. That's just a perceptron basically. Quadratic is unordered weighted gappy bigrams. This is just a standard result in SVMs. And Jean-Michel also tried using string subsequence kernels where you've got ordered weighted n-grams. In fact, this thing, we had hopes at one point it would give us more performance, but in fact it doesn't. It never gives anything extra. He's tried a couple more things since I last gave this talk. I'll have a slide about that in a minute.
So
yeah?
I have a question. When you say that the sentence is a point in RV plus one,
yeah,
that means that you have a bag of words model
yes.
on the sentence. So you just
weighted bag of words.
And yes, with each weight. So then at that point you've destroyed the sequence information in the sentence. How do you get the bigram or n-gram information that you need for the kernel?
Well, as I said, it's unordered. It's unordered Gappy bigrams. As I said, we tried this kernel, which doesn't destroy the sequence information.
Oh, I see. So the point in RV+1 does not apply to all the kernels?
No, sorry, you're right. It doesn't apply to this one. We never actually used this for the main experiment, so that's a good point. The slide's not okay. Correct. Yeah, that's right. So as I said here, we've got false accepts worse than false rejects. So there's two different technical approaches you can use when you're doing SVM. So there's this intrinsic parameter in the SVM formula where you can just weight the negatives more heavily than the positives. And you can also change the threshold. In the SVM literature, they call the first one intrinsic parameter, the second one recalibration. So we tried both those methods. We did these experiments with, here we've got a bit more than 10,000 recorded labeled examples. We did 10 random training test splits. And we varied, we tried different classifiers. We had simple threshold classifier, linear kernel, quadratic kernel. We tried different versions of the asymmetric costs, intrinsic parameter, recalibration. And we tried both our ground-based recognizer and our statistical recognizer. There's this folklore result that ground-based recognizers are better for doing open mic than statistical recognizers. I'll get into that in a minute. So we're looking at, in terms of performance metrics, we're looking at false rejects, how many false rejects we get, how many false accepts with misunderstandings, how many false accepts with crosstalk. So there's two things that can go wrong, right? If you don't reject, your basic choice is between accepting and rejecting. If you accept, you get it wrong if you accepted something that was misrecognized, and you'd also get it wrong if you accepted crosstalk. There's two basic reasons why you might not want to accept. And then we also looked at the task metric. The task metric is where we weight the different things by our weighting factors for saying false accepts are worse than false rejects. So our results look like this. We normalize the task metric, by the way. So everything it comes out as an error rate out of the maximum possible task error. So top two lines here, we use the simple threshold method. So we just have threshold and the confidence score. So here we get that we're getting on both the statistical language model and the ground-based language model, we're getting sort of roughly, well, here it's a bit less than 10, here it's more like 12. Error rates around about 12, 10%. On the task metric, we're getting about a 10% error rate on the SLM, 7% in the GLM. The reason why we get a bigger difference here than here is the false accept rate is much worse for the statistical language model. Now, when we use the linear SVM classifier, we immediately get a pretty large improvement. So the classification error, the average classification error over the three different categories here, goes down from 9.4 to 6.3%. Task error goes down from 7.0 to 6.2. And then, so going from here to here, that's just introducing an SVM instead of a threshold. And then we tweak the SVM. We can improve that quite a bit. So we go from linear to quadratic SVM. We go down from 6.3 to 5.3 on classification error, 6.2 to 5.7 on task error. And then when we do the recalibration, unfortunately, I just didn't have room to do both kinds of asymmetric. It turns out the recalibration method is slightly the better one. Actually, recalibration it actually increases the classification error because what it's doing is it's paying more attention to the false positives, which are worse. So as you see here, you increase the false reject rate from 2.7 to 4.3. You decrease the false accept rate from 6.8 to 4.7. And since the false accepts are worse than the false rejects, the task error improves again from 5.7 to 5.4. So you put all these things together, you see there's really quite a large improvement here from using the SVM method. So here we are, so summarizing. The average classification error with the best SVM method goes down from 9.4 to 5.4, it's 41 relative. And the task error from 7.0 to 5.4, 23% relative. And we saw we got small improvements with the quadratic kernel over here. So the quadratic kernel is a little bit better than the linear kernel, so you can see that the bigram information is helping you. And the recalibrated SVM is a bit better than plain, because we're moving the mistakes from the bad category to the good category. So Jean-Michel's still working on this, and he's made some more improvements recently, which we're still evaluating. It turns out Gaussian kernels are still better than quadratic kernels. You get a small improvement there. We tried to use the n best input instead of one best input, and again you get a small improvement on that. He's done experiments using the online passive-aggressive algorithm from Kobe Kramer and his collaborators, which is a good online approximation to SVM. It's just an approximation, so the results are slightly worse than for SVM, but it's much easier. It's got much better complexity characteristics. You can train much more quickly, and you can do more experiments. Fernando Pereira made this point in a talk he gave at ACL. He's working with Kobe Kramer at the moment. And we're also doing, as an empirical evaluation, estimation of the weighting factors. So trying to get actual numbers, what the relative costs of false positives and false negatives are. It's kind of tedious, because you have to do all the videotaping and measuring of looking at the videotapes and measuring things with stopwatch, but yeah, it'd be nice to get those numbers. So are there more questions on this before I get on to the last topic? Yeah.
Just watching you use the system, I noticed that your pattern in speaking, like maybe it's your speed or velocity or something, seemed to change as you talk to the system versus talk to us.
Yeah. I mean,
I wonder if you looked at any other parameters like speed or.
We should do that. Yeah, no, it's on our list. I think that's absolutely right. I think if we did try doing some of those parameters, we'd probably get further improvements. There was a paper by Oliver Lemon in last year's ACL where they did something like that, and that they reported it helps really. I should say that the version, as I was demoing, I said it's a deployed version. The version with SVM it's more accurate. But yeah, I thought you might want to see the actual thing. Okay, so I think we've just about enough time to do the last topic. So side effect-free dialogue management. This is basically a paper we gave at last year's ICSLP in Korea. So this is actually very generic stuff. I mean, it's not specific to Clarissa in any way. So here's a sort of picture of your generic dialogue management system. So speech manager, speech recognizer, an input manager, which is taking stuff both from speech recognizer and from other places in the environment. Stuff goes from the input manager to the dialogue manager, which is maintaining some sort of context. And then it goes to the output manager, which may be doing things like displaying things on a screen, speaking, making changes in the environment, which can go back to the input manager. So this is our generic spoken dialogue system architecture, and this box context is very important. So if you want to be able to do clean corrections and undos, it's all about context. Anything you do changes the context. So the context is both updated by the dialogue manager, and it supplies input to the dialogue manager. And the context could be things like discourse context. It generally includes both discourse context and task context. So, generic examples, you put it on the red block, it's probably from discourse context. The red block, you probably have to look at the scene to figure out which block you're referring to. So, very generically, you process dialogue moves, you change the context. And most systems, I mean, maybe I'm being unfair to people. Maybe there's more groups than us that have looked at this and tried to be more principled. But in most systems I've seen, the context is distributed throughout the program state. So changing the context is basically a side effect thing. And of course, if you start using side effects, systems always get harder to debug. And certainly on lots of the dialogue systems I've seen, it's hard to make the system modular. It's very hard to test the dialogue manager in isolation. Typically, you have to test the dialogue manager as part of the system as a whole, which leads to all sorts of problems. As I said, I'd be interested to hear examples of people who've done the same thing as us and made the dialogue manager into a completely side effect-free module, which can be tested on its own. But in my experience, that is really the exception. So what we wanted to do just very generically, was create a side effect-free dialog management module for a command and control act, in particular for Clarissa, where we'd handle the context declaratively, and in particular we'd handle the task context declaratively. And we expected the payoffs would be, first of all, that we'd be able to get more reversibility. In particular, we'd be able to do corrections and undos in a cleaner and simpler way. And secondly, we'd get more modularity, that the dialog manager, since it's a side effect-free module, could be tested as an isolated component without bringing in the rest of the system at the same time. So yeah, in the next few slides, I'm going to say how we did that. Actually, before I do that, when I say side effect-free dialog management here, a lot of people sort of immediately say, no, you can't do that. It's contradiction in terms. How could it be a dialog manager and be side effect-free? Because the dialog manager is doing things. And, well, it's a reasonable objection. And when I say side effect-free, what I really mean is that the dialog manager is separated out into a big piece, which is it's more than 95% of our dialog manager, which it's a relationship. It takes dialog moves as input, and it produces actions as output. It doesn't actually produce the actions, it produces specifications of the actions. And then you've got an execution module that actually carries out those actions. So as long as you quarantine the actual execution of the actions into this little corner of the dialog manager, you have the rest of the dialog manager just creating a relationship between descriptions of dialog moves, descriptions of actions, and it's not a contradiction in terms. You can have side effect-free dialog management. So we're using a version of the information state approach, which has been popularized by a bunch of people. I guess David Traum is the first person I think of, but other people working in that Trinity framework have done a lot of popularization of this. So your key concepts are states, dialog moves, and actions. So in Clarissa, a state is a vector of 25 components. So we've got dialog information, like most recent thing the system said, the currently salient objects. You've got task information, like where you are in the procedure and what the current output volume is. You've got a back pointer to the previous state. You've got an ID for the current state. There's other things as well, of course. And a dialog move, we have things, they're not quite the same as the list of semantic atoms that I showed you earlier. There's a small amount of post-processing that goes on. So a dialog move representation of go to step 2.1, we've got like go to brackets 2.1, continue will be one of these commands. Yeah, and the correction wrapper represents things like no I meant or no I said. And then actions, we have most actions are reversible actions, like you can load a procedure, you can unload it, you can navigate from one place in the procedure to another place, you can navigate back again, you can set a volume, you can unset it. And the only irreversible action the system is speaking. You can say something, but of course you can't unsay anything, as I guess everyone's learnt at some time, usually the hard way. Luckily, Clarissa doesn't ever have to unsay things. It's never really capable of offending anyone. So the dialog management update function, it's a function of the form dialog state times a dialog move goes to a dialog state and times a set of actions. So this is again the update semantics approach of people like Traum and David Traum and Robin Cooper and so on. And it's completely declarative. This is just a just a declarative relationship. And I guess what we've done here in Clarissa, which is novel, is we've extended this to include task information, not just the dialog information. And to tell the truth, I don't know whether this is completely novel. I just haven't seen anyone who's done it before or done it as systematically as we have. I saw David Traum not that long ago, and he didn't tell me that we got it wrong. So I guess maybe we're on safe ground. So technically, what we're doing here is we've got this update function f here, taking the dialog move and dialog state, the input state and the move, the output state and the actions. And we're decomposing that into smaller functions, g, h, no. So this is about distinguishing between irreversible actions and reversible actions. So here, g takes the input state of the dialog move and it produces the output state and a set of irreversible actions. So this is just the irreversible actions. And now the reversible actions we get from comparing the input state and the output state. So h is a function which takes the input state and the output state and compares them and looks at all the actions that you need to perform in order to get from the input state to the output state. And the ordering function is just something which takes the unordered set of actions and turns them into an ordered set. So we break down the f function into these three functions over here. And the way they fit together is like this. So we have G, remember this is the, it takes the input state and your dialog move, and it produces an output state S prime and a set of irreversible actions A1. And then you take the input state and the output state and apply the H function to it, and that gives you a set of reversible actions A2. And then you say that f of the whole update function, f of the input state and the dialog move is S prime, we get out of the G function, and an ordering on the set of irreversible actions A1 and set of reversible actions A2. So that's how these three functions, G, H, and O, fit together to make the f function. So here's an example. That was kind of abstract. So if you see an example, you see it's actually very simple. So here's a sort of scaled-down version of what's happening in Clarissa. So we say go to step 4.2, and here's our input state, ID 17. 17 is the ID of the input state. We're at location step 2.1 of the procedure. Our output volume is 60%, and this points back to the last state, state 16. And the G function creates state ID 18, location 4.2, because I go to 4.2, volume 60%, that stays the same, we haven't said anything about volume, and the last pointer points back to, oh, wait a minute. Yeah, it points back to 17 over here, that's right. And the irreversible action is, it says we are at step 4.2, or whatever it is, something like that. And then we use the H function to compare these two states. And we see the difference between those two states is that there's a location 2.1 here, location 4.2 here. So you need a navigation action to navigate from, to update the screen displays to point to step 4.2 instead of 2.1, which is this action over here. And that comes out of the function H. We completely modularize the two operations. First, this just creates a new state. This H is finding out what reversible action you need to get from this state to this state. So payoff for this is we can do very simple definitions of correction updates. If you look at our XLIP paper, there's a version of this in the Clarissa Tech report as well. I've got a point of that on the last slide of the talk. You can write simple formulas to define all the effects of all these correction moves. We write L of S is the previous state before the state S, and C of M is the move saying correction M. So if M is go to step 5, C of M is no, I meant to go to step 5. And then if we have, I don't know whether these formulas are really interesting, probably you want to look at these offline, but if we have G of the previous state of S, L of S, and the dialog move M goes to S prime A is a set of irreversible actions. So we have F of, so here we're applying the move correction of M on state S, and the result of that is S prime, that's the state you would have got from updating the previous state, and the ordering of the actions you get from the correction move on the move M on the previous state, and the H thing, the reversible moves you need to get from S to S prime, from the current state, the state you got to from performing M on the previous state. And again, if you look at an example, you see this is actually really simple. So I'm just continuing with the one we had before. We have here I said, I was at this step here, I said go to step 2.1, and now I say, no, I meant decrease volume. So decrease volume is we take the back pointer to here, and then we do the increase volume, so decrease volume action from here goes to here. So decrease volume changes the volume from 60% to 40%. Wait a minute, sorry?
Looks like those locations are backwards.
I think there's a typo here as well. Yes, you're right. That should be 4.2 there. The locations are definitely wrong. I'm sorry. That was no.
It should be 2.1. You reverse the first previous step and then you change.
No. There's definitely there's definitely a typo here. This should be 4.2.
This should be.
It's copy and paste error. Yeah.
I think you go back.
Originally, you were at 2.1, then you went to 4.2.
We're at 2.1 and 4. Oh, it's wrong in several. No. That's right. We're at. Hold on. Let's see. We're at, no. I think maybe it was right. I think I've got confused. We're at 2.1 and we're at 4.2. So here we are. We're at 4.2. Sorry, I'm getting confused. L points to the previous state. This is the previous state. Yeah. No, I was getting confused. The diagram was confusing me. Yeah, sorry. We're at 4.2. We say, no, I meant decrease volume. We follow the L pointer back to the previous state, which is over here, 2.1. We update this form using G to get location 2.1 and volume 40%. The back pointer goes to this state over here. Yeah, and the irreversible action is to say volume is now 40%, and the reversible actions you get from using H to compare this state and this state gets you navigate from 4.2 to 2.1. So we navigate because of this difference, and a set volume 0.4 because of this difference here. So
this approach has a problem. For example, if I say no, I meant decrease volume.
Yes.
And no, I meant increase volume. And it recognizes as no, I meant decrease volume. And you change to state 19. Okay, and then I say it again. No, I meant increased volume. Then you cannot go back to the correct state anymore.
Then let me see. Is that really right? I think, in fact, well, it's a.
Yes.
No, actually, it does. Why don't we just try this? Actually, well, first of all, let's look at it abstractly. Let me see. Did I actually get? Is this actually correct? Last 17. I wonder if this is actually correct. Last. No, it's pointing back to this state, right? It's pointing back to the previous one here. No, I meant decrease volume. All right. Let me just. It actually does multiple corrections. Why don't I just try running it so we can see? Load training procedure.
Do you want to restore the saved variable values?
No.
Starting procedure, Clarissa training, objective.
Stop.
Before step.
Go to step 2.3.
Step 2.3.
No, I meant increase volume.
A, go on. Output volume now set to 80%.
No, I meant decrease volume.
Output volume now set to 40%.
No, I meant go to step 4.1.
Step title, voice notes, timers, alarms.
No, I meant go to step 4.3.
Step 4.
No, I meant 4.5.
Say, give me step 4.
No, I meant 4.7.
The timer is now step 4.7.
Undo.
The set alarm command will undoing command. We are at objective.
Stop. So I think it's the pointers are actually. I agree. This is sufficiently confusing for some reason that, as you see, when I'm doing it, I'm getting confused myself. If you look at the formulas and trace the pointers out on paper, it's all completely clear. But it took us a couple of days to convince ourselves that it really was correct. I remember we got a little weirded out too. For some reason, it's one of these constructions that is actually very simple, but your mind doesn't quite process the pointers the way it should. I don't know why. I'll skip the second correction. So I'm out of time. So as I said, the other, well, it gives you this nice way of doing corrections and undos. I think the thing which is perhaps even more important is it lets you do sensible regression testing on the dialog manager. So in a side effectful framework, it's very difficult to do regression testing on dialog managers because you have sequences of commands where context is important. If one utterance in the sequence changes, then everything after that utterance changes too, and the other utterances the later ones are rendered invalid. So a side effect-free approach, you keep the context as part of your test suite example. Everything's side effect free. You can test each example in isolation with the context. So you can do modular tests of the dialog manager, which we found really very useful. And yeah, you can have a library of dialog examples with context. And the only way you can develop problems if you change the dialog manager so much the context objects are no longer valid, in which case you have to recompile your suite. But you don't do that very often in practice. So summary of that part of the thing is you've got this declarative approach to dialog management with dialog states or objects. And actually, I didn't say about confirmations. If you look in our XLIP paper and in the Clarissa Tech report, we show you do confirmations and it's also very straightforward. So confirmations, corrections, confirmations, and regression testing. So just to wrap up, since I really am out of time, I'm afraid. So we first used Clarissa on the ISS June 27th this year, and we ran the training procedure, which I showed you briefly, which actually runs nearly all the system functionality. So it's as far as we know, the first time anyone's ever used a spoken dialog system in space, which was nice. So we've got all the stuff logged. If you go to the Clarissa website, we've got a longer version of this report. We've got detailed analysis of where everything was. So the training procedure's got 50 steps. So all those steps, 45 steps with no problems. There's bad recognition due to the Russian cosmonaut talking loudly in the background on 4 steps. He was very close to the microphone, just behind Commander Phillips, and the recognizer got totally confused. Phillips had to repeat himself and correct. And there were 2 steps where he got confused about the command syntax. Yeah, so as you see, 90% of the steps, no problems, and he was able to sort things out. Performance per WAV file, we got 88 WAV files. They were commands, they were correct, the response was correct. 11 WAV files were non-commands, they were correctly ignored. And here are the bad ones. We got command with no response 9 times. I think at least half of those were when the Russian was talking in the background. And we got a command with incorrect response 5 times. I think it was, again, most of them background noise. So, not really enough to be statistically significant, but, anecdotally, it was quite a good result. And Phillips said he said it exceeded his expectations. He seemed pleased with it. The real test is whether they continue to fund the project. We'll find that out in the next month or so, but right now it looks good. So, yep, picture of the space station. If you want to find out more, the Clarissa website's at NASA. There's a Regulus website, SourceForge, and also at NASA, and there's a tech report you can get from ICSI Berkeley for various complicated reasons. I was technically working at ICSI throughout the course of this work. So that's it. Thank you very much. I think we took most of the questions throughout the talk, but if anything's left over.
There's plenty of slots if you want to talk to Mani in the afternoon, and you can join us for lunch too.
If you ever want to wait just 1 minute, I can give a very quick demo of the speech translator while you're here, or do you want to just break for lunch? Let me see if I can just switch to that. Let's see. We've done at Geneva University using the Regulus technology to build the recognizer. So I'll just show you some translation from English to French. Where is the pain? So this one's push to talk. So it recognized it, gives me feedback what understood. And why is it not speaking?
It was very soft.
No, but it's it was speaking before.
Try turning up the volume on your laptop.
Oh, maybe that's it. Let me have a look. Oh, yeah, you're right. It's still incredibly quiet. I'm sure it was louder.
Où avez-vous mal?
Is there any way to make this a bit louder?
That's fine.
Okay. Is the pain in the front of the head?
Avez-vous mal sur le devant de la tête?
Ah, thanks, that's better. And yeah, I can. These are all standard examination questions we got from doctors for investigating headaches. In the back of the head. So it's paraphrasing that back as the pain in the back of the head.
Avez-vous mal à l'arrière de la tête?
How often do you get headaches?
Quelle est la fréquence de vos maux de tête?
Do you have headaches every day?
Avez-vous vos maux de tête chaque jour?
And actually I can show what the representations look like here if you're curious. So we want to see what logical forms look like. Actually maybe not quite as many as that. That's just source representation enough. So you see this, the grammar is producing linguistically oriented feature value pairs. Yes, utterance, yes, no, question, you, voice active, tense present, have symptom, secondary symptom, headache, and so on. Do you usually get headaches in the morning?
Avez-vous habituellement vos maux de tête le matin?
Anyway, you get the idea. So we're totally out of time. I just thought I would show you the example, other things we could do with Regulus. But this one's got a vocabulary. It's actually 3 different subdomains. You could either headaches, chest pain, or abdominal pain. And the vocabulary is between about 400 and 550, depending on the subdomain. And it's trained on a...
One subdomain with that? No.
The picture is actually so you can click on the relevant part of the guy and you get that subdomain. And we have an enthusiastic Java hacker. And so it's one active subdomain at a time, that's right. And, it's trained off a very small amount of data. I think it's something between 550 and 700 utterances per subdomain. We've got a lot of different system languages and a lot of subdomains, so it's difficult to get large amounts of corpus data together. So it's exactly the same architecture. It's using Regulus to build the grammar and then PCFG, straightforward training of the CFG to turn to PCFG using the same training corpus.
For this task, I think you have very limited way to say things, right? Why can't you just do a direct mapping? Is it possible?
Well, the way we started off this project was we thought we'd start with the simplest possible architecture, fixed phrase, and then see if that was enough, and then enrich it as required. We did try fixed phrase, and in fact, it's really difficult to remember the phrases. You do need some flexibility. No, we experimented with fixed phrase and we gave up. It's just too restrictive. So we've done tests where we have people learn the system coverage by interacting with the help window.
So since you have the paraphrase here, you really don't need to do translation, right? If you have the paraphrase, you can do a direct mapping from paraphrase to the other language.
Well, it is doing that.
Okay.
It's template based, basically.
No, it's actually it's not really template based. It is doing linguistically motivated generation at the target end. Again, we started off with template based, but as you increase the coverage, you find there's more and more phenomena. So it sort of gravitated towards a linguistically oriented way of doing things. It was kind of interesting. We started off with things totally ad hoc, and linguistics came in successively. We found that actually linguistics it can be quite useful at times. We were pleasantly surprised. It's an interlingual-based system, yeah. Yeah, I mean, if probably should do it offline. If people are interested, I can show. We've got Japanese to English as well. We're demoing Japanese to English and Japanese to French at HLT later this week. We're doing that together with some people at NICT. And we've got several other languages in various degrees of readiness. English to Spanish is currently same domain.
So how do you? So that will be the user of the system will be the application.
Well, this application again, it came from talking to users. I mean, we had a doctor came to us and said that he would find this very useful for talking to foreign language patients. He was afraid he would kill someone one day through not understanding what they were saying. And he said if you just ask these standard questions with a little bit of variation, you can, most patients, you can just send them home and tell them to take an aspirin.
It's very limited.
It's limited, yeah. I mean, again, it's a safety-critical application where the doctors are much more interested in accuracy than in coverage. They told us that it has to be at least 99% accurate. They would like 100% accurate, but.
That's also why you have this paraphrase here.
Yes.
So the doctor wants to make sure what they understood.
The paraphrase is absolutely essential. The critical thing is how accurate is the translation from the paraphrase. That has to be very accurate. But I mean, this is the kind of application that the grammar-based architectures are good for. You have an expert user, an intelligent expert user, and a safety-critical domain. I think that's where the niche is.
Does the application also use identification grammar?
It's the same, absolutely the same recognition architecture. And this is also an open source system, so anyone wants to play with it, downloadable off the web.
Well, thank you.
Oh, thanks.